So I want to show you how to walk through the data analysis a little bit further than we had done before. So before, just to review, we had talked about finding mean, standard deviations, graphing those means and standard deviations, even finding the best fit line to describe the trend of data, um, and to determine whether or not there's a likely difference between any groups. So what I want to do now is show you how to do some hypothesis testing. And you need to remember that, again, in hypothesis testing, we're comparing two hypotheses. The alternative hypothesis is saying that there's going to be some change in your dependent variable because of the changes in your independent variable. Your null hypothesis saying is that there's no difference between your groups. And in science, we don't ever actually prove anything, because if we were to say that, then we could be easily embarrassed because we don't have all the pieces, and as soon as we discover something new, we could be proven incorrect. So really what we want to be doing is disproving ideas when the data doesn't match it. And we always go with the law of parsimony, also known as Occams Razor. The most parsimonious things are the simplest explanations for things. And unless we can rule those simple explanations out, those simple ones stand. I think the opposite would be easy to make sure you understand. If you think that a natural phenomenon is most easily explained by the most complicated working of it, then we don't really know what's going on. So we can start the other way though, and start with simple and start to rule out simple ideas when the data doesn't match it. So what we're going to do is try to find out if our null hypothesis can be disproven statistically. And so when I said we don't prove things, we also need to make sure that what we do know is that science isn't a free-for-all. It's not a flip of the coin kind of thing. We do have confidence levels, and I'll talk about that in just a few minutes. For chemistry and physics, you're going to need confidence levels probably in the order of 99%. But for biology, because we're talking about chemical processes or physical processes that are within organisms, and because there are lots of factors at play inside of an organism, it's not a simple reaction. We give ourselves a little bit more wiggle room. So biology is set at about 95% confidence level, and I'll show you what that means in a minute. So what I've done is taken that same data set. Here's that data set that we started with earlier in the previous video. All I did was took two groups, because I'm going to show you how to do a t-test, and then I'll show you how to do an ANOVA test. So the t-test is a test that compares the means and the spread of data around those means, or the standard deviations around those means, to one another statistically. So again, my null hypothesis would be that there is no difference in the change of mass of a potato between these two temperatures. Not that temperature doesn't affect it, but these two temperatures are not going to have a drastic effect on, or won't have an effect on, the change of mass in the potato. My alternative hypothesis might be that at the higher temperature, there will be a greater increase in the mass of the potato over time. All right, something like that. So what we need to do is a t-test, but we need to add in some data features in Excel, which you may or may not be able to do at home. If you can't do it at home, the computers at school certainly can do this. So what you will do is click on data and see if you have the add-in already. So when you click on data, what you would expect to see is something over here that says data analysis. I don't see it, so I'm going to walk you through how to install it. So I'm going to go to File, I'm going to go to Options, Add-ins, and what I see is that my inactive application add-ins include this Analysis Toolpak VBA. So I want to click that, and instead of hitting OK, I want to hit Go. I'm going to make sure I've got Analysis Toolpak VBA on. I'm going to hit OK. And let it load. And now I've got my data analysis button. Again, it's under the data tab. There's my data analysis button, which is great. So now I can click that, and I can choose the different tests that I might want to run. So we're going to talk about ANOVA in a few minutes. ANOVA is called analysis of variance, and you can do this for groups of more than two. So when you do your 5x5 model for science fair, 5 different levels of your independent variable, The ANOVA is the test that you're going to be using, but you want to make sure you understand what a t-test is as well. So I'm going to go to my t-test section down here, and there are 3 types. So I'm looking at, I need to look at what type I should be using. And really what we need to be looking at is either the paired 2-sample for means or the 2-sample assuming unequal variances. So this top one is really for testing if you were to use the same subjects like before and after a treatment, right? So if you were going to see what the effect of different temperatures are on, well, the thing about this with people, I don't want to give you too many ideas for your own science or project, but if I were to take a test of you, so what you knew about biology on day 1 and what you know about biology now, or even at the end of the year, I'd be comparing data points from what you knew to what you now know, and that would be paired sampling because those data points are paired together. They're not randomized, but these are different piece of potato. So I'm going to go with a 2-sample assuming unequal variance. I'm going to hit OK, and then this box pops up, and this is where I put my data in. So I want to include my labels, my top row of numbers. So I'm going to check that box. The alpha of 0.05 indicates that that's my margin of which I'm going to compare my data. So that 0.05 leaves 0.95 out of that number, and that 0.95 is going to indicate my confidence level of 95%. That's going to be really important because Excel is going to pump out the number I need to compare my calculated t-value to. And that's what a t-test will give me. So I'm going to put in my data, my t-test. I'm going to pick out my first set of data, my first group. I've picked the label because I've already told it will have the labels by checking this box, and then do the same thing for the other group. And these 2 groups do not have to have the same number of data points. That does not matter. And I can leave my hypothesized mean difference blank. But I don't want to put it in a new worksheet. I want to put it on this sheet so I can look at it all together nice and neat. I'm just going to pick a cell down there and hit OK and let it run. Oh, I didn't put my data range in. I need it down here. And I'm going to hit OK. Maybe I'll put it over here. Let me figure this out. Okay, so I figured it out. I was doing the wrong test. It shouldn't be equal variances. It should be unequal variance. I mean, should not be unequal variances. It should be equal variances. So I'll show you how I got to that. Let me delete that out of there. So I'm going to go back to my data analysis. I'm going to equal variances. I'm picking my groups, labels, 0.05. My output range is right here. I'm going to hit OK, and I get my data. Now this looks like a lot of information, and you could spend a lot of time analyzing it, or you can just use the pieces that I'm going to tell you that are really, really important. So what you need to know, so these means should match the values that you have up here. They're just rounded a little differently. We've got a variance value, so unless you know what that means and can discuss that in your data analysis, I would not worry about that. Your observations are your data points. We've got 5 data points. Your hypothesized mean difference is 0, so we're testing our null hypothesis. My degrees of freedom, that's what that stands for. So this is an important value. I'm going to highlight it. So this is going to be an important value to put into a table in a report. You would not print off your Excel spreadsheet and put that into your report. This is your workspace. From here, you can neaten things up, polish it up, and put that into your lab reports. But I want to highlight this for you so you know that this is important, not that it needs to be highlighted in your lab reports. Okay? So degrees of freedom are calculated, and I want you to write this down, by the total number of data points in each group, subtracting 1 from each group. So this group has 5 data points, so 5 minus 1 gives me 4. This one is 5 minus 1 gives me 4. You add them up and you get your degrees of freedom of 8. So then what we need to do is take, this actually will tell us a nice number, but I don't want you to check it with Excel because Excel sometimes gets a little off. So this T-stat is, I'm going to rewrite this as my calculated t-value. So this is the value that Excel has calculated for us, but it's not in the way that we want to, because what I did was compare 25 to 27. If you flipped it around, you would not get a negative number. So all I'm going to do is turn this into the positive number. So 0.987, right? So this is a nice long number. I've got 4 decimal places there. I don't want all these decimal places here, so I'm going to format that. So I've got my 4 decimal places. Right? So it matches the number of decimal places there, so I don't lose any points in my lab reports. And what we need to make sure that we understand is that we're looking for the t-critical two-tail value. If you have questions about that, please ask. So I'm going to highlight this cell, because that's the value that we need, and then we need this value as well. So if, this is the rule, if my calculated t-value is less than my t-critical two-tail value, so my calculated t-value is 0.9879, my t-critical two-tail value at a 95% confidence level, because that's what we set our alpha to be. I'm going to format this so it's 4 decimal places, 2.3060. Because this calculated t-value is less than this t-critical two-tail value, I can say that the difference between these two groups at 25 degrees and 27 degrees is, and this is an important word, not statistically significant at a 95% confidence level. That's really important language that you make sure you understand. We don't say insignificant statistics, we say not significant. So when we say there's a significant difference, that means statistically significant. And in biology, again, we're looking for the 95% confidence level. So I want you to be able to look at, I'm going to pull this in front of the screen here. So this is a T chart, a T table, and what you need to be able to do is know how to read this. So we've got our degrees of freedom over here. We've got to find our degrees of freedom. Remember, we calculated it to be 8, and so we're going to be looking at this row right here. So my calculated t-value is 0.98. Well, 0.98 is just above 0.71, but not yet above 1.4, right? So we're going to look at this column, this first column right here, as our value that we need to beat. So we know that 0.98 is greater than 0.71. So that tells us that there's a confidence level that our numbers are different, right? Our means are different, but that confidence level, if I scroll down here, this is the probability that chance alone could produce a difference. That's a 50% chance that there's a difference between the data and that there is a difference, or that it was just chance, it was random. And in science, again, it's not a flip of the coin. We need a greater confidence level than that. The number we're really looking for in biology are the numbers in this column with a 5% chance. So we're 95% confident that the difference in the independent variable is what caused the differences in the dependent variable. In biology, we give ourselves a little bit of wiggle room. In chemistry and physics, they probably use a 1% or maybe even a 0.1%. The greater that confidence, the better. So the number that we were really looking to beat is 2.31 at a 5% confidence level, which is what this number would round to, right? If we were rounding to 2 decimal places, 2.31. And so in order to make this statement complete, what you would say is that at a 95% confidence level, because the calculated t-value is 0.9879, and the t-critical two-tail value is 2.31, or 2.3060, there's not a significant difference between 25 and 27 degrees Celsius for the increase in the mass of the potato. It's a long sentence. but it's very clear to someone who's reading it technically, reading it with a technical lens of what that means, right? And so what you then need to say is that there is no difference between these groups. So sometimes when we're looking at the graph, we're looking at these two values here, 25 and 27, and despite the fact that these means are different, the value of those means are calculated to be different because of the 50% chance that is in play here, not because these standard deviation error bars are different from each other. But if you were to compare 27 to 29, you're likely to find a difference, and you could go through those steps and do that yourself, right, with the same data set. But let me show you how to do an ANOVA. And an ANOVA test is similar analysis, but it's with multiple groups. And it's a little bit easier to actually to run through the steps here. So again, I'm looking at my 5 data sets. I'm going to go to data. And again, we're doing now an ANOVA test. So instead of T's, we use something called F's. The value that's calculated is an F. So I'm going to go to an ANOVA single factor because you're having one independent variable here. We don't worry about replication. And then I'm going to put my input range, but I want labels. I want my alpha to be 0.05 again. But this only has one input range. Here you actually select all of the data that you want, and if you have blanks in there because they're uneven numbers in the groups, that's totally fine. It won't calculate that in there. And I want an output range, and let's see if it goes in there. Nope. Okay. It's going to have to go, I think, over here. Nope. I just changed my input range. On my output range over here. So the issue just to clarify what the issue is, it doesn't like to put this in the columns where there's other data. So I picked over here. This graph is sitting on top of my spreadsheet. So there's no data in these columns. And so what I have here, again, is my averages, my labels on my groups, the number of data points, and again, averages and variance. And we've got some. Again, I don't need all of this. What I need is the means and standard deviations as an own chart, and then the hypothesis testing data in another. So what ANOVA does is two things. It calculates the difference in between the groups and within the group. So it's looking at the variance within the group and then the variance between the groups, which is an important idea to make sure you square away in your head. So degrees of freedom are important. There are 5 groups. So between the groups, 5 minus 1 is 4. But within the groups, there are 25 data points. And because each group has 5, but remember 5 minus 1 is 4. And that's for each of the groups, so we get to 20 degrees of freedom. We have a calculated F value. This is my F calculated, or my calculated F value. Calculated F value. And then we have a p-value as well and an F critical, right? So there are 2 ways that you can do your analysis. And the p-value, you could do this with the t-test as well because that's calculated as well. You could see that in your chart. So again, we're going to be comparing your calculated F value to the F critical. Well, 47 is certainly bigger than 2.86. So you could say with a 95% or maybe even 99% confidence level, or beyond that, I'll help you figure that out in a second, you could say that there is a significant difference between or among your groups, and you need to say that your calculated F value is 47 and change, and your F critical is 2.86 and change. You got to change your decimal value so that they're consistent with your data, your process data. But what you don't know is where the difference is. You do not know which groups are different from each other. All this is saying is that there's some difference within your sample. If you find there's not a significant difference calculated through your ANOVA, that means none of your groups are different from each other, which only supports your null hypothesis. Here we've disproven our null hypothesis, which means that there's some difference in your data sets. Now it's a matter of you looking at your graph to determine where that difference might lie. That difference might be here between these two, but we've already done the t-test on that. So you know that these two groups are not different from each other. My next test would probably be between the 27 group and the 29 group. Do a t-test to find out if there's a difference there. And if that's the case, you know that there's a difference in the dependent variable between this range of data points for temperature and this range of points for temperature. And you might even want to do a t-test between 27 and 33, and do another one between 29 and 33 and 29 and 35. It really depends on how much analysis you need to do. That I can try to help you with, but you need to be concise and purposeful in your analysis, right? So let me highlight for you the data points that are useful from this, and that's these values right here. Now the p-value is important to think about. If you were to think about how this number gets written out, 6.69 times 10 to the negative 10, that's a lot of that's a dot with a lot of zeros, and then a 669 at the end of it, right? Because it's times negative to the 10. That's a really small value. That p-value we need to think about with our it's a probability value. Probability value that the chance is what's causing the difference. So that's a really small value, which means that we can be extremely confident that there's a difference amongst our data. So that actually tells you your confidence level. So if you calculate that value, and then subtract that number from 1, multiply by 100, you get your confidence level. And so you could say with this confidence level, as calculated by the p-value, there is a significant difference amongst your data. Then it's your job to figure out where that difference is to describe the data as it turns out in your lab. Okay? That's all part of data analysis. That's not yet about making conclusions. Okay? So it's right on the edge of starting to make conclusions. I hope that makes sense, and I will follow up with another video in which I do these steps in Google Sheets.